Let's now look at one of the difficulties of XFLR5, and that's the viscous analysis of planes and the errors that we can get when running this analysis. This is something usually which newcomers find a bit difficult to understand. To illustrate this, let's try to build a new plane with a new foil. So I'll use a good old Clark Y airfoil which I have in my database. So as usual, the first thing to do is to repanel this foil. Right, so let's repanel it. 121 nodes is good, but we'll change a bit the distribution, or maybe a little. 150 for a change. Apply. OK, and let's overwrite it. Right, now we have a sound airfoil which we can analyze and generate our polar mesh. We go to Xfoil direct analysis for that. Let's select the Clark Y and switch to the polar view. Show only the polars for this foil, and we shouldn't have any at this stage yet. Hide all polars. And suppose we do this a bit too quickly and we generate only a limited polar mesh. For instance, let's start with one. We do this manually, type 1. The polar mesh is necessarily type 1. 100,000, OK. And sequence from 0 to 7, analyze, and from 0 to -3. OK, this is our first polar. Let's generate a second at 200,000. OK, same as before, and up to 7. And another one which will be 300,000. OK. Now we have our polar mesh, but it's not as extended as it was before, and this may create some issues when we run the plane analysis. So we still use this plane, but we're going to change the airfoil. So let's duplicate it with a Clark Y. Okay, let's edit this plane, or rather we'll go straight to edit wing. Change this to Clark Y, Clark Y, Clark Y. There we are. Okay, let's look at it sideways. Yep, that looks like a Clark Y. Let's change its color so that we can recognize it. There we are. Oops. Looks good. Okay, and save and close. Here's our Clark Y airfoil. It still has the masses of the original airplane, just a different foil. And now we can try to run this analysis. We'll run the type 2 analysis using the plane's inertia, leaving everything else unchanged. And let's say we want to run it from -3 degrees to 15 degrees by increments of 2 degrees. Right, let's pull up the log file, or let's first have a look at the curve. Well, it didn't generate much, you see. We only have one point here and nothing else, whereas we expected a polar ranging from -3 to 15. So obviously something went badly wrong. And to understand what went wrong, we bring up the log file by typing L on the keyboard. There we are. So what's the problem? -3 degrees, we have a negative lift, so it makes sense. The plane won't fly, so there's no result for this AOA. At -1 degree, the plane will fly at 24 meters per second, but something else went wrong. Let's see. What went wrong is that at we have at the span position at the tip we have a Reynolds number of 175,000 and a lift coefficient of 0.04, and obviously this could not be interpolated. To understand why this occurred, let's go back to our foil analysis and the polar mesh, and we can see that 0.04 here, the curves do not extend downwards to 0.04, and if they do not, well, the results cannot be interpolated. The viscous part cannot be deduced from these polar mesh. So what we need to do is extend these curves to more negative values by running each of them for the Clark Y, let's say down to -7 degrees or -10 degrees, whatever. Okay, now we have a curve going much lower, down to -0.4, meaning that the airfoil is not capable of producing lift coefficients lower than 0.4. Let's do this for the other two. -10 is not necessary, -7, there we are, and on the third one we could also extend in the upper CL range if we wanted to, but that's not necessary. And let's go back now to direct plane analysis and see if things are getting better. Right, we have 3 points now, which is a bit of an improvement. Let's check again. So we got these 2 points here. Sorry, we only have 2 points, and then we have an issue because at the tip of this wing we have a Reynolds number of 83,000 with lift coefficient 0.14 deduced from the VLM, and the program could not deduce viscous properties, viscous drag, from these values. So let's check again, go back to direct foil analysis, and indeed we've been a bit sloppy and we didn't generate any curve for a Reynolds number less than 100,000. So let's do that now. We generate a new curve and let's put 50,000 for instance. Okay, and create this curve and up to 10 degrees. So this is our new curve. A bit surprising. I'm a bit puzzled that the drag is less than at higher Reynolds. Oh yeah, this is the AG25, my mistake. Current polar, delete, yes, and let's go back to the Clark Y and create the same polar for 50,000. There we are. Oops. So what does it look like? Yes, we have now our polar at 50,000. This should help the plane analysis. We can switch back to the plane analysis, run again the thing, and this time we have a good curve ranging from something like -1 to 9 degrees. Still, we couldn't generate points at higher AOAs or lower than 1 degree. Let's see why. Well, at -3 we have a negative lift, so that's understandable, and at 11 degrees we have, for Reynolds number of 60,000 to 80,000, we have very high lift values, and we didn't extend our polar mesh to values up to 1.24, which explains why we couldn't get some results. Now, as you can see, the VLM is a linear method and it will produce increasing lift coefficients with increasing AOAs up to unrealistic values. Due to viscous behavior of the fluid, of the air, we have stall behavior much before we reach these values. And that's what the airfoil analysis tells us, the X-foil analysis tells us. So we could try to extend our polar mesh up to higher values, but X-foil probably could not find results, even if we tried to. Lift coefficients for Clark-Y, which could reach 1.54. And what we have to keep in mind is that the VLM really is meant for low AOAs in this range here. We could try to understand and analyze what's going on here, but the results would be less meaning than they are in this range here. The VLM, the panel methods are really used to compare performances in this range of AOA. Okay, well, that's the explanation of the viscous errors, the errors we can get when we run viscous analysis.